My name is Luis Capagnai. I'm the engineering manager for Myro Industries. And this presentation that we're going to go over today is on the code requirements for rooftop equipment and their supports. This presentation does not cover any Myro product specifically, but we'll go over the code requirements for anything that needs to meet any wind, seismic, or snow, or even international building code requirements here in the United States. Our objectives for today are, we're going to identify who's actually responsible for the design of rooftop equipment and their supports. We're going to identify common issues observed on rooftops caused by rooftop equipment and the supports that go on top. We're going to look at FEMA post-natural disaster event assessments and how they factor into the codes. We're going to discuss code requirements for accessibility, equipment support placement, and loading, and then how industry standards are factored into the codes. We're also going to go over deferred submittals and delegated designs and what information is needed to complete a code compliant deferred submittal. And then we're also going to look at examples of completed projects and how those code requirements can be addressed. So let's get started. Who's actually responsible for rooftop equipment and supports? This is a question that we get asked all the time from professionals such as mechanical, electrical, plumbing, structural, and architects. We get this question asked because it is something that is not directly shown in the codes on how to go about it. So we're going to go over that right now. This first column are the individuals who are working on a project. Everyone involved or shown here in this first column should understand that there are code requirements when looking at the building as a whole. Most of these people don't understand, though, there are code requirements specific to rooftop equipment. What we want to happen is that everyone in this list understands those requirements. The only way for us to do that is to have the requirements shown in the specifications and in the drawings. So who can do that? The people who can actually dictate those requirements fall under the professionals in charge of the project. That will mainly fall under the mechanical, electrical, and plumbing engineers because the components that are being supported on the roof will typically fall under one of these scopes. The structural engineer of record also has a huge say in these code requirements. Unfortunately, it's not usually a structural engineer who gets to call this out on drawings. Once again, it usually falls under the engineer scope whose components are being supported, such as a mechanical, electrical, or plumbing system. An architect of record also can dictate the requirements and specify and put in drawings these code requirements. But once again, these may be general, just as with the structural engineer, may be general requirements when the actual shown drawings and the actual code callouts for the mechanical systems, electrical systems, and plumbing systems will once again come from those MEP scopes. A specialty engineer, such as myself, I consider myself a specialty engineer, doesn't typically get to say or dictate or somehow facilitate those requirements. A specialty engineer will be the one who will actually enforce those requirements through an analysis. Once again, no one in this list is actually enforcing the codes, but a specialty engineer will usually be the one who will take on that responsibility and liability to do the analysis. So it's just a nice little loop. The mechanical, electrical, and plumbing engineers will call out in their specs and in their drawings the code requirements necessary and show how they're going to be met, but they will say, you need to contact this engineer or an engineer who's licensed in the state, usually a specialty engineer, to do this specific type of analysis. After that is completed, it will be the structural engineer of record who will look over that analysis completed by the specialty engineer to make sure that the building can withstand those applied loads. What we don't want to happen is that in our specs and in our drawings on projects here in the United States, it says by others, or it doesn't say anything, that it just leaves it open for anyone on this list over here to go and do whatever they want. We really want people to focus on the actual code requirements for rooftop equipment supports. And hopefully these rooftop code requirements are something new to you, and that's what we're going to go over today. Very, very important that this gets done and gets completed. But once again, it's up to the people in this column to make sure that everyone else on the project understands these requirements. So why is this such a big deal? Why do we have codes and standards for rooftop equipment supports? The purpose of the International Building Code, which is the main code that we're going to go over today, is to establish a minimum level of safety. When it comes to rooftop equipment supports, we want people who are in the building, people who go on top of the building, and bystanders outside the building to be safe. that they don't get hurt from something that falls or flies off the roof, or it gets hurt in some other way when they're accessing the roof itself. So that is reason number one. We want people to be safe. The reason number two on why we have codes for and standards for rooftop equipment supports is so that the building remains in use. And I'm going to give some examples of the building remaining in use right now. Building remaining in use is we don't want to have to shut down a building or have to replace supports or replace rooftop components or the roof itself because something wasn't installed correctly, wasn't analyzed by an engineer licensed in the state who knows what the roof is able to handle. Some examples of that: small expansion and contraction. It's unfortunately pulling up this membrane and abrasing it, so we can have water intrusion after this occurs. Even small wind loads, shown here on this condensate drain. Unfortunately, once again, this little support, these are wood supports or field fabricated supports, something that was built out in the field, unfortunately, is also pulling up this membrane. And we can't have this happen because water starts to come inside the building. Also, a lot of wood interaction with different types of membrane can be negative, where we actually have deterioration from upper membranes just from the interaction or leaching with wood. Right here on the right is the most common issue. And once again, this is the building remaining in use. Most common issue that we see in industry is from ponding, or we have an excessive concentrated load in one small area where water, snow, or ice starts to build up around these supports. Unfortunately, this crushes the insulation. It usually punctures or stretches the membrane enough where we're going to have water start to infiltrate through the building. And then once again, no one really notices there's an issue up on top of the roof until someone sees water seeping through their ceiling. So once again, this is the second reason, or the number two reason, on why we have codes for rooftop equipment supports, so that we don't have to replace or go and fix items or even the building itself because correct supports were not installed from the beginning. The reason number one, though, as I said, is that safety aspect. This was a FEMA assessment after Hurricane Ivan. This was a very large 18,000-pound HVAC unit that was strapped to a curb up on top of this roof. Unfortunately, no codes or any code analysis was done for this rooftop equipment unit. And when the wind speeds came in this area, they were only estimated to be between 85 and 95 mile an hour winds, which for reference is on the very, very low end. When we're looking at California, Oregon, and Washington and our low wind states, this is not even hitting the lowest required minimum wind loads in those areas. So even with these smaller wind loads, this unit actually came off this roof. It fell in this parking lot. And fortunately, in this FEMA assessment, no one was injured or hurt. But we just want to once again impress on your mind, the reason why we have these codes is mainly for that safety aspect. I keep talking about the codes. And as I said before, mainly everything we're going to talk about today stems off the International Building Code. There are different releases of the International Building Code that we can use on any given design, but it must be the building code that's adopted by that local jurisdiction or state, sometimes as necessary, to use in that design. So they all need to meet a project-specific design criteria, which once again will go off that local jurisdictional adopted code. That means some states or even some counties or cities might still be using an older edition, such as the 2012 or 2015 code. We have most of the states and jurisdictions looking at the 2021 and 2018 IBC, but we even have some that have adopted newer codes. Depending on the project site, once again, along with that jurisdiction, will depend on the code that will be referenced that we'll be using in analysis. Within these codes, in the International Building Code, we also have reference codes, such as the mechanical code, which we're going to go over in depth today, the plumbing code, fuel and gas code, etc. There's many other codes that will have references to rooftop equipment supports. And just to state here, this is a general presentation to meet the International Building Code requirements. When it comes to each state will have their own adopted building or construction code that will cover rooftop equipment supports. Rooftop equipment supports in those state adopted codes will almost usually adopt word for word those code requirements that we're going to go over in the international standards today. So once again, you can look at your own state adopted codes, but for rooftop equipment supports, they will be almost word for word these requirements that we're going to go over here shortly. Within those codes, unfortunately, they won't tell you what those wind loads are or what the snow load's going to be, or if you have seismic in your area, what those seismic parameters will be. These codes will then reference a different code, which is ASCE 7. ASCE 7, just like the international standards, will have different releases that will be called out and referenced within each international standard. These ASCE 7, American Society of Civil Engineers, will have those wind loads, those associated snow loads, and seismic parameters for every single location in the United States. So once again, this is where we get the requirements called out, but they will reference these standards as well as these codes on where we're actually going to be applying these loads, what those loads are actually going to be. So once again, these are what the codes, when I say codes, I'm talking about these. We also have to take into account industry standards depending on the type of components and the type of roof that we're going to be working with. For example, if we have duct up on a roof, we're going to be using SMACNA, the Sheet Metal Association, on what type of materials we can use, what type of weight this is going to be, how far apart we can space our supports that are up on top of the roof from one another. If we're going to be using some sort of hazardous materials such as ammonia, we're going to have to look at ASHRAE or IIAR2 for those recommendations on how far apart we can space supports, the type of materials we can use. Same thing with pipe hangers, if we have any insurance standards or roofing manual standards. And then once again, too, how we're actually going to connect these supports that are going to meet wind and seismic loads back to the building. Is it a wood deck, a concrete deck, or a steel deck? We're going to be using different standards for all of these different type of applications. So once again, it's not just the codes that need to be followed, but within the codes, they have standards that we need to use depending on the type of materials that we're going to use, the type of components that are being supported, and the type of roof that there will be supported on. These are the standards that need to be taken into play. And then, of course, also we need to look at the safety standards. We're not going to go over OSHA code requirements today when it comes to surefoot access or maintenance access up on top of a roof. But just remember, it is there. We will call out the reference here in a few slides on what that is in OSHA 1910. We're going to go over the International Mechanical Code standards for safety and maintenance accessibility. But just remember, this is a big requirement. This does drive a lot of what we do, and it's the OSHA codes, and we can do that in a separate presentation. But safety standards also need to take into play. And to finish up here in this first section, question number 1. I have a few questions throughout this presentation to drive a few topics home that we get asked all the time from professionals. And this first question is, who's actually responsible for ensuring code compliance with rooftop supports? And the follow-up question to that is, why do we have codes for rooftop equipment supports? And that answer is, everyone involved in the process is responsible to make sure the code is followed. But once again, everyone may not understand that there are codes for it. So the main directors or facilitators to help everyone understand those code requirements falls under the mechanical, electrical, and plumbing engineers for the components being supported on the roof, the structural engineer of record, and the architect of record. These are the people who can specify and put in drawings the code requirements. And then why do we have these codes? The codes are there to ensure that safety is met and to maintain the building operation. First off, in the International Mechanical Code, since most equipment that we're going to find up on top of roofs will fall under something to do with the mechanical code, if not directly with the mechanical, wind resistance. In section 301, it tells us that any mechanical equipment, appliances, and their supports that are exposed to wind shall be designed and installed to resist those wind pressures, according with the International Building Code. With the wind section, there are no exemptions. There should be no exclusions, and this has to be included on any design that's going to meet the International Mechanical Code or Building Code standards for rooftop equipment supports. They need to be designed to meet wind. And we're going to find out in a little bit in the International Building Code, this has to be analyzed by a licensed professional engineer for that state. Continuing on in the seismic resistance section, it's where earthquake loads are applicable in accordance with that IDC. Then the mechanical systems need to be designed and installed to resist those seismic forces according to that same code. So this is a little bit different with the seismic resistance compared to wind. Seismic can be exempt in many regions in the United States. Different from wind, where wind unfortunately cannot be exempt If it's exposed to wind on the exterior of the building, it needs to be designed and installed to resist those wind pressures. So why? Why is there such a difference between wind and seismic? Obviously, seismic or earthquake loads are applicable in those earthquake-prone regions, but wind resistance should be taken into account everywhere in the United States. This is a great example of that. This was just a simple roof. This is in the Rockies, not near a hurricane, tornado, large, tropical storm region. This was up in the Rockies. There's some snow on the ground, nothing crazy. What occurred here was a wind event happened on this building or near this building. In the surrounding area, no one knew that a wind event had occurred. It was just a windy day, nothing more. But the correct wind condition came across this roof. And unfortunately, that lateral wind condition came and hit these pipes on their side and it tipped them over. These were being supported by filled fabricated supports. A good indicator of that, once again, we see some wood blocking here, but these supports had actually been installed and had been supporting these pipes for years and nothing had ever happened. But the correct condition came across, the wind hit these pipes laterally, and unfortunately, it damaged most of these pipes where we even see a lot of these pipes had actually burst on the side where they had taken this picture. We can still see the steam coming out. So once again, wind can never be exempt regardless of where we're at in the United States. Following some other FEMA observations to look at. This one here was a windscreen related event. The codes, and I'm looking down here, do not allow for any reductions in design wind loading due to apparent shielding from adjacent structures. In other words, even if you have a windscreen or architectural screen or tall building, a tall wall, a large air handling unit next to your components that are on the roof, unfortunately, you can't reduce the wind load saying, hey, this big object is going to shield my, my other components on the roof from the wind. Unfortunately, we have to act. If there's anything that's up on top of the roof, even if it looks like it's going to be shielded, it has to act as though it's being hit by the wind full and head on by the ultimate wind speed that we'll find in the code. This is a great example because someone had installed a windscreen and unfortunately had reduced the wind loads behind this windscreen for this mechanical and plumbing equipment. But when the wind actually came, it came over this first wall. And when it hit the wall, it came over the top and created somewhat of a turbulent or uplift force effect. That actually picked up this equipment that was behind the wall, knocked it into the windscreen on the opposite side, and most of the equipment actually blew off the roof. So once again, there can be no reductions in wind loading due to apparent shielding. If it's exposed to wind, it has to meet those wind pressures head on. This is another FEMA observation. This was after Hurricane Katrina when this assessment was done. This building actually held up fine to the small amount of flooding that was in the area, as well as the wind loads. The engineer of record, the structural engineer of record, designed this building, and it actually held up in that regard. The issue that came and why they were doing this assessment on this building was there were mechanical units that were up on top of the roof that were not installed or even engineered to meet the wind loads in the area. When the winds actually came, these mechanical units started whipping around the roof and unfortunately created incisions in the membrane. When the rain came after that wind event, the rain actually infiltrated this building from the roof membrane down through the building. And it did it so much that they actually had to condemn the structure due to the flooding occurring from the roof down and not from any of the flooding that had been mitigated down at the ground level. So once again, even in small wind situations, or regardless of where we're at in the United States, wind always has to be taken into account, and there are no exemptions for that in any of the codes. Continuing on in the International Mechanical Code, some other important things that we need to take into account when we're looking at the code requirements for rooftop equipment supports is that interval spacing. And we're going to focus on pipe support spacing right now. In Table 305.4, it tells us, based on the piping material, what our maximum horizontal spacing can be in feet. Most items we'll find on top of the roof from mechanical and plumbing systems will be made out of steel pipe. You cannot exceed 12 foot on center from one support to another. It has to be a maximum of 12 feet. If you have PVC or copper, for example, those will be based on not only the material, but also the diameter of the pipe. And those can decrease significantly. And then, as I said before, based on the contents, that may also change your interval spacing. For example, in the International Fuel and Gas Code, if you have gas up on top of a roof, that maximum spacing, even though you might be using a steel pipe, might change anywhere from 4 to 10 feet, depending on the diameter of the pipe. So once again, we'll look at the contents, but in general, we'll be using this piping support spacing for most roofs. Unfortunately, this isn't always followed. And this is a great example of this code not being followed in Table 305.4 of the Mechanical Code. The contractor, unfortunately, had exceeded the maximum support spacing intervals for the chilled and hot water pipes that were being supported on top of these supports that they had made. They had made these out of structural steel and even welded these connections, but unfortunately, since they had exceeded that support spacing intervals, it put more of a load on these supports than they could handle. And a lot of these actually started to bend and twist and even broke their connections at the welds. That was issue number one. Issue number two was that they didn't analyze what this was going to be doing to the roof below these feet. And we can see here, there's some wood block, another good indicator. This is field fabricated, not done by an engineer. And once again, believe it or not, wood blocking is still the number one competitor to meeting code requirements for any type of rooftop equipment support. Wood is still being used today, and unfortunately, most people don't know that it can be hazardous or detrimental to the building or to even people's health and safety. Unfortunately, with this dead load, it was exceeding the maximum dead load allowed for most roofs, which is 3.0 psi. There are ASTM standards that state you can have a 20 psi load on some roofs. Unfortunately, most people don't know that that is only for dynamic loading, for someone walking across a roof, getting from point A to point B. But the maximum allowable load for most roofs in the US is 3.0 psi. Some of them may not exceed 2.0 psi, depending on the type of rigid insulation or membrane. This one, unfortunately, they had exceeded it. Every single support location, unfortunately, had damaged the roof severely and had caused a lot of water damage inside the building because of the roof punctures. So once again, we want to make sure we're below that 3.0 psi limit, and we're also not exceeding that maximum support spacing interval. Here's another example of someone who had unfortunately exceeded that maximum support spacing interval per the Mechanical Code. The frame here in the middle of the run was the first frame they believed to fail. It had so much weight on it that the frame started to twist, it buckled, and when that first frame failed, the subsequent frames on each side of it had excess weight that they could not hold, and they also failed down the line. They unfortunately had to keep students out of this building due to safety concerns from this pipe sitting up on top of the roof until they could get the correct piping support system installed for this pipe run. So once again, looking at the piping support spacing interval, very, very important to follow that code. Also in the Mechanical Code, it talks about thermal expansion and contraction needs to be taken into account. This is a great way to do it. This is more of an industry standard that's being added or even adopted into a lot of great designs where people can actually put on some sort of roller this way, where we have any type of metal system, such as this metal pipe, it's going to be expanding and contracting. Most of the time we're thinking, hey, if it's a gas line or a hot water, chilled water line, glycol, something that's going to have a lot of temperature variance from the ambient temperature compared to the content of the pipe, that's when we need this. We need to remember it can happen for any type of materials that can expand and contract due to temperature variance. This is an example of some electrical conduits that unfortunately also had expanded and contracted enough that where they were tied down to meet the wind loads in the area, which was great, unfortunately, they actually broke at their links or couplers. And we found out that there was an issue here on this roof, or the building owner did, because this conduit and this tubing unfortunately started to abrase the electrical wire inside. When it did that, it actually created a fire, and that's how they found out there was an issue. Thankfully, it was able to be mitigated, and it was very small. But I believe they had to replace every single electrical wire, or all the wiring on top of this roof, because all of it had been exposed to the elements and it was no longer protected. So once again, it can be anything within our mechanical, electrical, or plumbing systems. We need to make sure that we're allowing for that natural movement. Going to the safety maintenance accessibility, we're going to look at the Mechanical Code, as I said, but OSHA 1910 subpart D, walking working surfaces, is the main contributor to when we're looking at making a safe, accessible place of work. We need to be looking at OSHA. That will give us the height requirements, that will give us all the requirements for people going from point A to point B. But looking at the mechanical code, just so we don't have this is super dangerous. We don't want people climbing under, climbing over, getting cut on anything, exposed edges. In the International Mechanical Code, here in red of section 306, if there is an obstruction that's greater than 30 inches in height, or if we have roof slopes that are greater than 33%, then we need to provide proper access. Proper access looks like this. Here's a great example. We didn't want people going under, or at least I believe this was an inspector call out where they didn't want people going under or climbing over all these obstructions on the roof. So they provided these crossovers and platforms to get from point A to point B. These are also made to meet the wind and seismic resistance in the area. They're tied down to do that. Here's another example of that. Unfortunately, this is a good bad example. Here we have a crossover on the top, getting over all the obstructions, which was done in the end because they unfortunately had installed some crossovers where you had to step on some distribution lines. And even when you got to the upper platform here, you had to duck under items as well, which unfortunately is against that code. So once again, provide the proper type of access, make sure you're following the OSHA regulations and standards along with the mechanical code callouts that we need to do. Continuing on the International Building Code, now that we've gone over the mechanical code. International Building Code, in addition to wind and seismic forces, we need to look at dead loads, live loads, and snow loads. These are also loads that may come into impact a design that's up on top of the roof. We have to also look at the type of roofing system and how we're going to attach that system to the structure. We know, and we have to follow the code where it tells us we have to have a project-specific design criteria. And this will make sense looking at these pictures. We can't, unfortunately, just use whatever type, and unfortunately in this situation, they were using some metal feet that just were on top of this membrane or, this rubber blocking, which unfortunately did not interact well with those systems. Also here, if we're looking at attachment for those attached supports, we can't have a system that is going to meet a metal deck, for example, this open web joist system, and go and take that same support and go and attach it to a concrete deck, or take a concrete deck and go apply it to a precast double T deck. They all have to have their own specific design, where they're going to have a specific anchor or fastener or bolt, whatever it may be, or even to a wood deck. They're all going to differ, and it differs quite a bit, as along with the support spacing and where we can actually put them. So everything has to have a specific design criteria met for the building that we're looking at. One big thing with this and the codes is that we need to understand that these codes are continually evolving. As I mentioned, in the International Building Code, we also need to look at snow. Snow has always been in the codes, but a lot of people didn't know how to follow that before, or even for engineers, specialty engineers, we didn't know exactly what they were looking for. We would do our own analyses, but it varied from individual to individual. Now the codes actually tell us, in a more recent edition of the International Building Code and even ASC 7, we can now see what we're supposed to do. With smaller pipes, we need to account for snow accumulating in this way, and it actually gives us these equations to figure these out. Larger pipes, we need to look at snow accumulating in this way, which is a more realistic approach to how snow actually accumulates on pipes, cable trays, or ducts up on top of a roof. Even if we have a component on top of the roof that's next to another component, we need to do some math to figure out if snow can actually bridge or cornice, taking account for that gap now that might be filled with snow, which we need to account for additional weight. So some super awesome things. Once again, the codes are continually evolving. We need to make sure, as I showed in that slide in the first section, there's so many different codes and different releases. We need to make sure that we're following the one that applies to that jurisdiction or to that state that we're working in, and make sure that we are going to follow the standards that apply to that code as well. In the International Building Code and ASC 7, just like the mechanical code, we need to look at seismic loading. Seismic loading, we need to look at not only a horizontal component, but we need to look at a vertical component as well. Continuing on in these verbiage sections, it tells us that any non-structural components and their supports that are attached or anchored to the structure need to meet these seismic loads, or excuse me, the seismic loads need to be attached or anchored to the structure if it's a non-structural component. Continuing on, any attachments need to be bolted, welded, or otherwise positively fastened without consideration of frictional resistance produced by the effects of gravity. In other words, if we're going to meet the IBC and ASE 7 standards, in addition to the mechanical code standard, if it needs to meet seismic, it has to have positive attachment, which is something that we see vary quite a lot in a lot of people's specifications and drawings, is that it might say meet the seismic load or meet the wind load, but no penetrations are allowed, or do not penetrate the roof, which unfortunately goes against what the code is saying here. So remember, there is no way to actually get around seismic without having a positive penetration back to the building. Seismic rarely ever controls any design that we do for rooftop equipment supports. It's always going to be wind. Wind is always going to be a much, much higher load. Even more so with wind, there has to be some sort of positive attachment to counteract those reactions that we'll get from the wind loads. All right, to finish up this section, question number 2. According to the International Building Code, what type of loading can be exempt from an engineering analysis for rooftop supports if we're only looking at dead, seismic, and wind? And the answer is seismic. Seismic is the only one that can be exempt, but dead loads and wind loads can never be exempt, reduced, or excluded from a rooftop support design that is actually going to meet the codes and meet the codes in that jurisdiction. And that's what I have here for you today in this second section. If you have any questions, we'll stop here. In the International Building Code, it also talks about wind loading, just like the mechanical code. And in here, it also tells us that we need to account for a potential lateral load and a potential uplift load. So as we went before in these examples, even if we have windscreens or any other type of shielding object, unfortunately, we can't reduce those wind loads. If it's exposed to wind, we need to act as if the wind is hitting these items head on. And along with that, we need to make sure that we're accounting for those uplift forces along with the lateral forces. And then I have a question down here, which leads into the next slide. How might a prevailing or gusty wind affect a design? And for those of you who are unfamiliar with a prevailing wind is just a natural occurring trade wind you're going to see over and over, year after year or month after month. It's going to be higher at certain times and lower at certain times, but you're going to see that natural occurring wind over and over in one area. So how might this prevailing or trade wind affect a design that meets the codes? And the answer is a prevailing wind should never meet or it will never meet a code requirement. And you should never do a design that meets a prevailing wind. This is a great example of someone who tried to use a wind load to meet a prevailing wind. Unfortunately, they had installed these mechanical units up here on these curves, and they were doing it and attaching these to meet this prevailing wind. Unfortunately, when that prevailing wind actually came to this building, it came on this lower section, it hit the upper roof, and it created an uplift force when it came to the upper section. That uplift force actually picked these mechanical units up and dropped them where we see they are in this picture. They didn't slide, they actually picked them up and dropped them. The other unfortunate event about this prevailing wind was that it occurred 2 days after these mechanical units were craned up on top of this roof. Once again, as with previous instances, no one knew in the area that there was a wind event. It was just a windy day. But this occurred, unfortunately, even with those low prevailing winds. So once again, we need to meet the ultimate wind speeds that we find in the code. There can be no reductions in wind loading, even if we say this is what we typically see in one area, because those do not account for any additional uplift or lateral forces that may be created around or on top of a roof structure. Going into deferred submittals and delegated designs, we aren't going to go into depth on what it says here. If you need or if you want, we're going to show you multiple slides with text on them, and we can send these to you. These are generic. This is not calling out any specific manufacturer or individuals. These are just the minimum requirements to meet the International Building Code for passing off responsibility or liability from design professional to design professional. The deferred submittal and delegated design sections are just for that. We take on the liability as design engineers or as specialty engineers from someone else who has actually given us this liability or this design to take on. A deferred submittal will come from an engineer or even an architect where they are saying, as a professional, I am deferring this submittal to someone else down the line to come and pick up. The delegated design is where we see the general contractor takes on that responsibility to go and find or seek out or even use the individuals that were called out in the deferred submittal to take on this load. This load will take on any type of component that's up on top of the roof, but this is the way that you're supposed to do it according to the building code. Have a deferred submittal from a mechanical, electrical, plumbing, structural, or architect. Send it, and when it's to the general contractor and they're awarded the project after the RFP has been issued, they take on the responsibility now to make sure that this gets done and completed by a professional engineer who's licensed in that jurisdiction and who can actually do this type of work. Once that is done, we need to make sure that the deferred submittals that are being done by those specialty engineers have at minimum the following. They need to have calculations showing loading and how it's applied to the frames. There need to be drawings that show how the frames are to be built, what materials are to be used, and their connection details back to the structure. There also needs to be a roof layout showing where the frames are intended to be installed and where they're going to be supporting those components. And then all these items need to be stamped by a licensed professional engineer in that jurisdiction. If we don't have these, that's where we get these awesome support designs, I guess you can say. Unfortunately, these are not correct deferred submittal designs. This one up here, one of my favorites, this was not on a school roof. Someone just needed the correct slope in their gas line and they put this football under it because it was available. This one right here, another one of my favorites, someone got done with their lunch or their break and they decided they could use their Mr. Cool Cup to go and support this condensate drain. Unfortunately, if you can tell, this is actually the high point in this drain now. No correct drainage is occurring. But even though this is essentially weightless when compared to other components on top of the roof, if it's not made to be up on top of the roof, it hasn't been analyzed by an engineer, it can still cause damage to the roof, which it did in this case. So once again, people can get very crafty. If we leave it open and say by others, we can see all sorts of items on top of the roof. And unfortunately, since you all as the professionals who are doing this type of work, if you do not pass that liability on to someone else and have them stamp it and engineer it to meet the loads in that area, you will be the ones liable if something occurs and if damage occurs up on top of the roof or if there's a safety concern. Aside from everything we've talked about, let's look at what can impact a design. The size, the weight, the spacing, and the layout of the components being supported along with their elevation off the roof will impact a design. Any type of loading also will impact a design, as we went over, specifically dead loads, wind loads, seismic loads, and snow loads. There can be additional loads such as live loads or even ice loads, but for the most part, this is what we're going to see up on top of roofs. Are we finding the codes directly, or are we finding the requirements directly in the codes for the design criteria? Are we looking at the structural engineering notes? Is it a local building code that we're having to follow, or officials telling us what those codes should be? Or are we looking directly in ASE 7? And then what are these loads being transferred to? Is the roof and the roof deck, the roof structure down below? How are we going to be able to meet those wind and seismic loads? That's what we're looking at. What materials are we actually going to use to support those components is also very important. As I said, wood, unfortunately, is still being used, but there are other components, even pre-galv or electrogalv systems, unfortunately, can break down fairly quickly over time. So we need to make sure whatever materials are being used, they will actually be able to be in use for the time that we've determined that will meet that code. Finishing up in this section, question number 3. What of the following should be included in a deferred submittal? Should it be calculations showing loading to the frames, shop drawings including the frames and how they're built, the materials used and how they're connected back to the structure? Should it be a roof layout where the frames are intended to be installed, or a PE stamped compiled engineering submittal? And obviously, I know most of you are all professionals. Obviously, the answer is all the above. But believe it or not, as a specialty engineer in this industry, I get to see other people's and other engineers' designs that they have stamped. And unfortunately, a lot of the designs I get to see do not include any of these three first items. And it's just a PE stamped submittal, and it just has some basic drawings with nothing that's been attached or meeting wind or seismic loads. So once again, remember, whoever you're passing this off to, make sure that they are competent and they are going to be able to follow the codes and that they understand what those code requirements and those standards are for whatever you're going to be supporting. And that should do it for this section. Once again, if you have any questions, feel free to stop this and then we'll continue afterward. We are going to go over a structural design criteria example and then some pictures of some examples of code compliant rooftop supports. This was a loaded example where we went through it and we took a lower wind speed, or just kind of an average low wind speed that you'll find here in the US, along with a very high loaded seismic design that you might find in a very high seismic region for any type of rooftop equipment support design. Going through this analysis, and we're going to show you something very specific that I like to pull out here. We are able to find that for a support that we also loaded in this mimic example, that for a trade pipe size of 6 inches, Schedule 40 steel pipe with liquid contents, that had 3 inches of insulation around this pipe, and it was supported at a tributary length of every 10 feet. So every 10 feet, we had a support supporting this 6-inch line. The dead load that we needed to account for in the analysis was 323 pounds. The horizontal wind force was 660 pounds of wind, and the uplift force that needed to be accounted for was 521 pounds. So once again, this is kind of in that average lower wind speed you might find in the US. Even in the high seismic area, the controlling horizontal and vertical seismic factors were only 258 pounds and 103 pounds of force. Compared to the wind loads, the seismic loads are much lower. When we're actually going through these designs, we have to use load combinations, which when we're looking at the International Building Code and ASC 7, show us that we can't ever actually have a seismic and a wind load in the same load combination, meaning these individual scientists and engineers who have written these codes have determined that we're not going to have a wind event at the same time we have an earthquake. We can have snow at the same time as we have a wind event, or snow at the same time we have a seismic event. But within these load combinations, it will either be governed by a dead load combined with a wind load, or a dead load combined with a seismic load and maybe some other factor. So here we show the correct loading combinations that need to be applied for those loads that we just looked at in that last slide. And on this example, we had a number of pipes that we had to load up on top of this structure and on top of this system. And here we're showing the dead loads, the wind loads, uplift load, lateral seismic, and vertical seismic loads. From there, we can determine what type of members are needed. So in this analysis, now we're determining what type of materials will be needed to use as the support structure. From there, we can figure out the attachment details, including the base plate, the weld necessary for the stanchion support, along with the interaction and how it's going to be connecting back down to the structure or the building below. And then from there, there should be cut sheets showing what materials are being used, how they're going to be supported, that support spacing, along with where they're being supported on top of this support structure, along with the connection details back to the building. All of that, along with their notes and material callouts, should also include a layout showing where all these frames are intended to be installed. And then all of this can then be stamped by a licensed professional engineer. There's a lot more that goes into the analysis, and there's hopefully a lot more calculations showing where those loads came from, how they're being applied, the inputs and outputs, along with any type of interaction analyses. But this is just a shortened version of what that should look like. So this is the example even for the layout. Here are some examples just to kind of finish up. engineered submittals that are code compliant. Two things I want to point out. Item number one, here there are stanchions. Stanchions are easily in my opinion, the best way to still meet the codes and be as least invasive to the roof as possible. A lot of different states and jurisdictions or even companies will like to use curves or even flash in these large mounted structures that you have to flash around on top of the building. Unfortunately, when we have large curves or other type of wood or flashing caps up on top of roofs, there's a good way for a lot of water or intrusion to happen, once again, with snow, ice, and water to get inside the building. We will and as I said, when we're going through this, as specialty engineers, like to be as least invasive as possible. We've gone through a number of these designs where we've been able to use stanchions. This is standard pipe, and we've seen other leading industry engineers do this as well, where you could use a boot cap or a boot flash, easily flashed around. You can find most of these at simple hardware stores even, that most roofers love to work with. Once again, this is not something where you're going to have a roofer up there for hours and hours doing one support. Easily flashed around and least invasive method. Along with these stanchions though, now you can have your base plate attached down to the building structure as needed to meet those wind and seismic loads. So that's the first thing I want to point out. The least invasive method is usually using some sort of standard stanchion pipe that will just go through the membrane once they have that hole cut out and attach the base plate down to the structure. Other item, number two, that I want to point out here is we just went over in the code that we have to have some sort of positive attachment for our supports that are up on top of the roof to meet the wind and or seismic loads. What I'm showing here, though, is that there are a lot of free-floating or sleeper bases up here on top of these roofs. The codes allow for this, and the codes allow for value engineered solutions or VE solutions, where the engineer in charge of the analysis, if he or she can determine that at these stanchion locations or at the attached locations that they can hold or withstand those wind and seismic loads, then intermediate supports can be used to help out with dead load and snow load distribution only. So those are the only loads that these free floaters will take on, and the stanchions will help take on the dead, snow, include though the wind and seismic loads if seismic is applicable. So these are good examples of that. And here's another good example, once again, going back to the expansion and contraction issue. If there needs to be an expansion and contraction on top of a roof, this is a great way to do it. These are roller supports or roller chairs. Roller chairs will allow for that natural movement day in and day out linearly. But if you have pipe guides that have been wind or seismic rated to meet those loads in the area, they can be attached to those chairs, transfer those loads to the header, down to the stanchion, and then attach to the structure where they will transfer those loads back to the building. So this is a great way to do that, once again, if you need expanding and contraction capabilities for your system. This is another great example of code compliance. These were ammonia lines up on top of a roof. These supports look a little bit different because when we had to go through this analysis, we had to use a more stringent and up-to-date code, which had more interaction because the importance factor for these supports actually went up in the design. So once again, it not only needs to meet the local codes, but it needs to meet the code and the standards for whatever components are being supported up on top of the structure. To finish off here, question number 4, in a code compliant rooftop support design, does every support need to be attached to the roof to meet the code? And the answer is no, but this is only after the engineer who's in charge of the design has determined the necessary spacing and frame loading is adequate enough to handle those applied loads and that they're meeting the codes to their fullest at that correct interval spacing. And that's what I have for you today. In summary, the building codes have been established and are going to continue to evolve as a base point to limit the risk to life and disrupt, observe failures, or make sure that that building remains in use. Standards developed by the industries are best practices on how to meet the code once it's called out in those code to help, once again, ensure that safety is met, and make sure that the building maintains its operation. The design and installation of rooftop equipment supports is addressed in the building codes. And unfortunately, there's no way to get around it unless we have supports that are inside the building that may only have to meet a seismic and dead load requirement. Floating supports alone generally do not satisfy any building code requirements. And then once again, it is up to us as the professionals on a given project where rooftop equipment support is present to make sure that it's either called out in the specs or in the drawings so that everyone on the whole entire build team can understand that there are code requirements for these special type of items. And that's what I have for you today. If you have any other questions or comments, please ask them at this time to your local rep or whoever is giving this presentation. If you have any other questions or comments or want to coordinate on any type of engineering design, feel free to reach out. We would love to help you out in any of your designs or anything that you have in the future. Thank you for your time.